You got one of these. Our lithograph we're doing tonight is the Bubble Nebula, also known as NGC 7635. And it's a beautiful, beautiful blue bubble of a nebula blown by that star in the center there. And if you want to understand how this all happens, you can turn over on the back, and there are a few paragraphs explaining what's going on in this nebula. Tonight's talk will be initial exoplanet discoveries with TESS. And I will say that I heard a whole bunch about the TESS discoveries last week. I'm waiting for Scott here tonight to clarify them for me so I really understand them, because I was at the American Astronomical Society meeting last week, and it's a whirlwind week. You get presented so many results. It'll be nice to be able to sit back and relax and really enjoy Scott's talk tonight. Next month, February, we have Your Place in the Stars from Amaya Morrow Martin here at Space Telescope. And in March and April, we have the infamous TBA, which means actually that it's very hard to pigeonhole astronomers to commit before the holidays. So now that it's past the holidays and past the AAS meeting, I can actually start getting them to commit, and I will fill out the calendar for the rest of the year. All right, please check the website. Oh, what website, you say? Well, here. This is our website for the public lecture series. If you go to your favorite search engine and type in Space Telescope Public Lecture Series, you'll find this, which has the link to the upcoming lectures over here. It has our links to our live webcasting, as well as our past lectures, all the way back to 2005 for some of them, although those are low resolution stuff. The stuff since 2014 is all the high resolution HD stuff. And you can also sign up for our email list. Speaking of our email list, these are just announcements that we do once or twice a month to tell you of the next lecture and where the other lectures, when the lectures are webcast and at that archive is posted, etc. And so far, we haven't had any spam. Yay! If you have comments or questions, you can send them to us at publiclecture@stsci.edu. Okay, social media. Hubble, the James Webb Space Telescope, and the Space Telescope Science Institute have the variety of Facebook and Twitter and YouTube and Instagram. And myself, I do a tiny bit on Facebook, Google+, and Twitter if you are so interested. Now, across the street, we have the Maryland Space Grant Observatory. And every month we ask them, are you going to be open tonight? Unfortunately, tonight there is ice on the roof that leads to the observatory, and they were told they cannot have a public group like this come over when there's ice until that gets cleared off. So they do have open houses on Friday evenings. If you go to md.spacegrant.org, you can find this webpage where they talk about the observatory status, and by like 5:30 on Friday evenings, they post whether or not they'll be doing observing there. So sorry, no observing tonight, but please check the website for more. And now, our news from the universe for January 2019. I get to say a new year, 2019. All right, our first story tonight. Star clusters within galaxy clusters. I was actually just having a discussion with one of our writers today. She was just getting annoyed with having to write the word cluster so many times, and it can mean so many different things. Well, let's start with the star clusters, because this is the globular star cluster Messier 80. And these globular star clusters are the really rich, big star clusters. They can contain as few as like 10,000 stars, as many as 100,000 stars, or even a few million stars. These are giant star clusters. And these are really good tracers of star clusters because because they can be so massive, they can be seen very bright. Okay? Now, when we're talking galaxy clusters, one of the most famous is the Coma cluster of galaxies. Coma is one of the biggest galaxy clusters out there. Galaxy clusters contain hundreds to thousands to even 10,000 galaxies. Coma contains several thousand galaxies, and it's located about 300 million light years away. So, what's the connection between these star clusters and these galaxy clusters? Well, inside galaxy clusters, we get a lot of this, galaxy collisions. Because you have a dense environment for galaxies, the galaxies can interact, they can collide, okay? And two things happen. One, we have evidence from computer simulations, this is a visualization of a computer simulation, that during these galaxy collisions, globular star cluster-like things can be created. So in the tidal tail of this galaxy here, you can see these white dots, okay? And in this tidal tail, you can see these white dots. And the computer simulations show that these look like globular clusters. So that you can create globular clusters during galaxy collisions. The other thing that happens in galaxy collisions is that these star clusters actually become disassociated with the galaxies. Okay? Because they can actually get flung out to large distances, and they are no longer bound to an individual galaxy, but instead they're spread throughout the galaxy cluster. So, could we look for star clusters within galaxy clusters? And remember, coma is 300 million light years away. What telescope could possibly have the incredibly exquisite resolution to be able to see globular clusters in a galaxy cluster 300 million light years away? Of course, it's everyone's favorite, Hubble. This image is, what is it? This image is like 25,000 by 16,000 pixels. So that orange rectangle I put there, that is a full HD 2 million pixel 1920 by 1080 resolution. Let me blow that up for you. So I blow up that orange rectangle there. This is what Hubble actually sees at full resolution. That's kind of cool for something 300 million light years away. Now, can you see anything that might be a globular star cluster? There are all these little dots there. And they could be stars in our own Milky Way galaxy that just happen to be in the foreground. They could be star clusters in coma, or they could be galaxies way in the background. Who knows? Well, a research group went in and they did a cluster finding algorithm to determine what all these little dots are. And the answer is most of them are globular star clusters. Yes, every green circle identifies one globular star cluster in the coma cluster of galaxies. So that's just one small portion of that image. If we go out to the entire image, there are 22,429 globular star clusters found in the coma cluster with this new survey. That's kind of cool. We're looking 300 million light years away, and we're finding over 22,000 globular star clusters. That's a huge population to study. You can do all sorts of cool things with that kind of population. But, as I said before, these star clusters have disassociated from their individual galaxies, and they're now associated with the whole cluster. And that gives you something else you can do, which is our second story. So the second story is visible tracers of dark matter. So we're not going to talk about the coma cluster, although this can be done for the coma cluster too. We're going to talk about the galaxy cluster Abell S1063. It's part of the Frontier Fields program, okay? And this is a galaxy cluster that's so massive, it has gravitational lensing. There's so much mass warps the space, and you can see these streaky, archy things here. Those are gravitational lenses. Now, gravitational lenses are due to the mass, and if you measure the amount of gravitational lensing, you can understand the mass. So here is the cluster as seen from the Hubble image. Here is a map showing you a lot of the gravitational lensing effects that they've uncovered here. And from those measurements of gravitational lensing, they can then create a mass map of the cluster. And this is the mass map of the cluster, showing you the contour lines of the mass inside the cluster. Now, the cluster mass is dominated 80% by dark matter. Right? The galaxies are tracers of it in some way, but they're only 20%. The normal matter is at most 20% of the material in this cluster. So we're trying to figure out where this dark matter is. So by using gravitational lensing, we can get an idea of where it is. But that's sort of an indirect method because we're measuring the gravitational lensing to infer the mass distribution. Wouldn't it be cool if we had some light luminous stuff that sort of spread across the entire galaxy cluster that could tell us what the potential of the cluster is, like those star clusters we just discussed? So what the team did is they went into that Hubble image and they went very carefully into it to try and get rid of all the normal light and pull out that very faint background light, the very faint intra-cluster light, the light between the galaxies, okay? And when they did that, they're able to pull out that blue map there. So this is the galaxy cluster image with that blue map being that intra-cluster light, inferred from things like these star clusters that are orbiting within the galaxy cluster. And using this, they could use this as a tracer of the mass. Because they also have a gravitational lensing mass map, they can correlate the two, and they find that it correlates extremely well. So this very faint intra-cluster light that they can, and certain clusters of galaxies relate to the mass map by gravitational lensing, uses that as a calibration to show that for other clusters, they can take that intra-cluster light and then use that as a visible tracer of the dark matter in galaxy clusters. Kind of cool. All right. Finally, our third story, which I could not ignore, contact in the Kuiper Belt. So, yes, the New Horizons mission was launched in 2006. And it went past Jupiter, and it spent basically almost 9 years, getting out to the Pluto-Charon system. Okay? And in July of 2015, they did a flyby of Pluto and Charon and Nix and Hydra, and I forget what the other ones are called. Styx and Kerberos. Yes. All 6 objects in the Pluto-Charon system, and they're able to get amazing things. And they had a great success, and they're out there, and they're out exploring the Kuiper Belt, and they said, we want to do more, okay? Because this is actually the first mission to the Kuiper Belt, okay? And they said, please, can we do more? And, well, NASA, of course, says, well, what are you going to look at? They go, oh, yeah, okay. Hubble, can you help us? So Hubble went and looked. And Hubble went out and found a bunch of Kuiper Belt objects. These ones in the green circles here, this is the motion of those objects over a period of time. That's how Hubble finds things in the solar system. It just looks, and anything that stays stationary is way distant. Anything that starts moving is inside the solar system. It found a couple candidate Kuiper Belt objects. And eventually they found one that worked for the New Horizons mission, so they didn't have to use too much fuel to steer towards it. And appeared to be some object that might be of interest. It was called 2014 MU69. Yeah, that just rolls off the tongue. 2014 MU69, yes. So the folks who run the mission said, you know what? We want to give it a nickname. They ran a contest, and its nickname is Ultima Thule. I have no idea if that's how you pronounce it. It's supposed to be pronounced, but it's just so much fun to say. It's Ultima Thule. So they redirected the mission to pass by 2014 MU69 when? On January 1st, 2019. But they still wanted to know what they were going to find. They had, because with Pluto, we had 60 years of observations to understand what we were going to find. We had almost no observations. You saw the dots, right? Yeah, it doesn't tell you much. So what they did is they went around the globe and they found places where MU69 would actually occult a star. All right, and the star's light would drop when it passed over and then rise back up. And so they actually had teams at differing latitudes watching during the occultation. And those down here didn't see any occultation. Those up here didn't see any occultation. Here, they saw an occultation from here to here, here to here, here to here. And what you get is an actual map of the shape of Ultima Thule on the Earth from the occultations. They went down and they mapped out the shape, the expected shape of Ultima Thule using occultations. And it was just amazing work. Mark Buey gave a talk here a few weeks ago. And he actually was so confident of this, he made a 3D model of what he expected Ultima Thule to look like before the encounter. And when the encounter happened, here he is showing his model against the observations. Is this guy good or what? Okay? Unbelievable that they predicted very accurately using these occultations the shape of Ultima Thule. That's one of the low resolutions image from Lori on the way in, but when they had time to get more data, here's what it looked like. That is our snowman in the Kuiper Belt, basically. It is a contact binary. Why I call so it means that this object here and this object here obviously formed separately, but then smonked together like two snowballs, and formed a snowman that's floating around in the Kuiper Belt 4 billion miles away from you. And the real hope here is that the study of this will teach us a bit about the early solar system, because when we have comets that come into the inner solar system, they melt and the gases flow away and the ices flow away, and they've been changed a lot. This object, hopefully, it's sitting out there in the main Kuiper Belt, out at 40 astronomical units away, probably has not undergone that much change in the 4.5 billion year history of the solar system. So the hope is when they study what the surface, the information from the surface of this, that they will begin to understand a bit about the protosolar nebula and the initial composition of the objects that formed in the solar system. Okay? And just because it's a contact binary, and they nicknamed the small one Thule and the large one Ultima. Okay? So our snowman has a nickname. We will not call him Parson Brown. We'll call him Ultima Thule. All right? And just for comparison, here is that same image of Ultima Thule compared to comet nuclei, the most famous being this is the nuclei of Comet Halley. It's 9.3 miles across, where this is 21 miles across. Okay, Temple, Borreley, Wild, and Hartley too. You can see it has these interesting shapes. And that's really what most of the objects in the Kuiper Belt are. They are what would be comet nuclei, but they're way out at the edge of the solar system. They're icy and slightly rocky objects that if they got kicked into the inner solar system, they would become comets. Okay, so they're, I guess you would call them dormant cometary nuclei. However, this one, being out there for all things, hopefully it will teach us about the pristine solar system, where all the things on the right teaches us about the solar system as it's been evolved through and over time and changed. Okay, so that was our New Year's resolution, that we got resolution of Ultima Thule in astronomy. Yes?
How close did it get?
Like 5,000 miles or something like that. I mean, this is not the highest resolution image it will have back. The data rate from 40 astronomical units is much less than America Online used to be 3 decades ago. Yeah, I mean, we're getting bits per second, not kilobits per second, okay? Not even megabits per second, bits per second type data rate. So it will take 14 months for all of the data from the encounter to get down. Okay, so they'll get some really good stuff starting soon. It went behind the sun from our perspective, so we couldn't get data for a while. It's now back. They're starting to get the data coming down. So be patient. We'll know more about this in 6 to 9 months.
Okay. That's reflected light, right?
Yes, that is reflected light. It does not shine on its own.
Yes. 30 AUs.
40 AU. 40 AU. Yes.
So that's contact, like the Jupiter kept things from forming in the Mars asteroid belt. Any planetary formations still maybe going on in the outer loop?
Well, the Kuiper Belt, at least the inner edge of it, is heavily governed by Neptune's mass. Neptune's at 30 AU, and we have a strong cutoff in the distribution of objects at 30 AU. There's also a strong cutoff at 50 AU. And that's not as fully explained. Okay? There could be another planetary type object. Folks know that there's a search on for Planet 9, but that's in a totally different orbit. I'm not sure that would affect the 50 AU cutoff, because that's way out there, like 75, 100 AU type thing. I'm not a Kuiper Belt specialist, but I know in talking to one of them, Mike Brown and I went to graduate school together. He was like, no, there really is a strong cutoff around 50 AU. And usually there's some gravitational interaction that will cause that. I don't know of one, but maybe I'm just ignorant on that. Okay.
Yeah.
Yes.
I remember a thing called the Oort cloud. How does that
Yes.
relate to the Kuiper Belt?
Okay. How does the Oort cloud relate to the? So the Kuiper Belt is in the plane of the solar system, and it's a belt. It's fluffy, but it's mostly flat. Okay, and that goes out 30 to 50 AU. The Oort cloud is much bigger. It starts around 2,000 AU and goes out to maybe 50,000 AU, and that's roughly spherical. Okay, whereas the Kuiper Belt is the genesis of the short period comets. The Oort cloud is the genesis of the long period comets. Comets that are more than 200 years are called long period comets. That have orbits less than 200 years are called short period comets. So we believe the reservoir of where the short period comets come from is the Kuiper Belt. The long period comets come from the Oort cloud. And a lot of the Oort cloud things, basically, how they got out there was they're scattered out of the solar system by Jupiter 4.5 billion years ago. Okay. I don't want to take up too much of Scott's time. If you have more questions, you can come down and ask me. But let's see. Which number are you? One. You are one. Okay. So, are we up? It hasn't. They connect. All right, I'm going to let you introduce yourself because I've already talked way too long here. Ladies and gentlemen, the incredible, the inimitable is going to talk about some really cool things, Dr. Scott Fleming.
Thank you very much, everyone. It looks like my mic's good. So I want to echo Frank's thanks for all you coming out on a cold night in January to hear about a very new mission, TESS. And also, I want to say hello and welcome to people watching online. I also want to thank Frank for a fantastic, by accident, background information on comets and clusters, because believe it or not, even though I'll be presenting the most exciting results on exoplanets, I have slides involving clusters and comets as well. So that was a fantastic job. So tonight, I'll be sharing with you some information on the TESS spacecraft. I figured I would start by describing the spacecraft and explaining what the spacecraft's doing now and how it's doing its science. I'll do a very quick summary of some of the very early results, and I'll highlight with the first 3 exoplanets that TESS has not only found, but confirmed to be actual objects. First, though, some boring stuff, me. I figured I would introduce myself a little bit because Space Telescope's very large. There's more than 500 and some odd people here at the minimum. It's growing, it seems like, every day. So I figured I'd explain what my role is here at Space Telescope before we get into the mission. So Space Telescope does a number of things. Most of you probably know that we're the Science Operations Center for the Hubble Space Telescope. We're going to be the Operations Center for the James Webb Space Telescope. We have an outreach department that does a lot to communicate a lot of the science results being discovered by telescopes. We have a lot of software developers who are making astronomy software for astronomers to use to analyze data. And another thing we do is actually serve as an archive, which is where I work, for data from a variety of missions. So I work at the Mikulski Archive for Space Telescopes. It's part of the Space Telescope Science Institute. And it actually has data from more than 20 different missions. Most of them NASA missions that flew in space. We have data ranging all the way from the 1970s with the International Ultraviolet Explorer all the way to TESS now, which just had its first data release 6 weeks ago. So part of my job, working with more than 30 different astronomers, developers, and engineers in my branch, is to make sure that all this data are kept not only for a few weeks or a few years, but for decades, and available for people all around the world to make use of from all these different missions that we collect. So let's talk about TESS. It wouldn't be a NASA mission without an acronym. And TESS is indeed an acronym. It's not, as far as I know, named after an individual. It stands for the Transiting Exoplanet Survey Satellite. And in fact, the acronym is a great summary of what TESS is. It's a satellite. It's specifically a space telescope conducting a survey for transiting exoplanets. And when I refer to the word exoplanet or extrasolar planet, what I'm referring to are planets orbiting stars outside our solar system. Just so that everyone's clear on what I mean by that. There's a couple of primary science objectives. One of them is to search more than 200,000 nearby stars to detect new extrasolar planets. And the key word is nearby, and we'll talk about that more toward the end of the talk. Another objective is using ground-based follow-up data to measure the masses for at least 50 planets that are smaller than about 4 times the size of the Earth. That's another objective. And the third objective is actually to play a sort of, in collaboration with the James Webb Space Telescope, TESS will identify some of the best exoplanets orbiting the brightest nearby stars so that when James Webb launches in a couple of years, it will be able to do one of its key science drivers, to not only study the exoplanets as a whole, but to measure some of their chemical compositions in their atmospheres. A very challenging measurement, one that we have done from the ground and even with Hubble Space Telescope. But James Webb, because of the size and the type of data that we'll get, will revolutionize our ability to not only detect planets around other stars, but measure what their atmospheres are like. And this is a key step in understanding the broader question of life in our universe. Real quick, there's a variety of institutions involved in the mission. The science operations are controlled by primarily MIT and Harvard, but there are also dozens of astronomers in dozens of institutions around the world working together to do the science operations of the spacecraft. Northrop Grumman was responsible for the sort of the payload and engineering parts of it, and then Space Telescope, working with our friends at the NASA Exoplanet Science Institute in California, serve as the archives, the final resting place for this valuable data the spacecraft is collecting, downloading, and being made public. So I had to start with one of my favorite things still, a launch.
8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff. The SpaceX Falcon 9 carrying TESS, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
So that was just a quick clip of the launch, which happened in April, just about a few months ago. It was a nearly flawless launch by SpaceX. It was actually the first time SpaceX launched a science telescope for NASA. Previously, most, if not all, of its supply missions had been deliveries to the International Space Station. But it was a perfect launch, and the spacecraft is healthy and in a great spot. But there's a second launch, and this is where we come in. This is when the data go public. So this is some social media tweets that I collected in my scrapbook. We had the first launch of data from the TESS mission to the astronomical community just this past December, just about 6 weeks ago. You can see some people were trying to call it TESSmas, since it happened a few weeks before Christmas, and people were hungry for this data. You can see people tweeting their screenshots of the page I wrote with their coffee, saying, "Where is it?" And I'm saying, "It's coming, give me a second." December 6th was very busy for us, but everything went successfully. Astronomers around the world were waiting for this. Has anybody heard of the Zooniverse project or Planet Hunters or any of the citizen science projects in the past? If any of you are familiar with those, there's a group in Oxford in England who are making the data public for citizen scientists to be able to look at the data and help us classify all the interesting signals. And they were able to download data from us and get data in their sort of interface on the web for citizen scientists to look at within 4 hours of us going live. It's a record. It's amazing. Other fun stuff, about a week later, this is where the comets come in. Some group at Washington was trying to figure out what's going on with one particular star, and this poor star, not only does it end up having, it's sitting there trying to shine and measure its brightness, but what they found was not only does this star have one asteroid come across and sort of get in the way, but then later, during the same observation, a completely independent and second asteroid comes across right in front of the star and ruins their ability to measure the flux of the star. But the bonus science is people interested in studying comets and asteroids get all these nice pictures to be able to study asteroids and comets. So it was a fantastic launch. In the first week, we estimate we delivered at least 100 terabytes of test data to more than 950 astronomers around the entire globe. So let's go back to the spacecraft. This is a movie that shows where how TESS sort of orbits around the Earth, which is located here in the center of your screen. And then the moon is this gray orbit here. And you'll notice that TESS orbits inclined relative to the Earth and the Moon. So it sort of dips above and below the plane of the Earth-Moon system. While the other thing you'll notice is that the orbit is not circular. It's somewhat elliptical. And this is by design. It's actually a very stable orbit. And during the blue parts of the orbit, TESS is staring at one part of the sky, collecting lots of data on the brightness of all the targets in its field of view. And then when it dips down to the, when it dips down to the orange part of the orbit, it actually downloads its data to Earth as fast as possible, where the bandwidth between us and the radio stations is maximized. Not quite as hard of a problem as New Horizons, but there's a lot of data. It takes about 2 weeks for the spacecraft to go all the way around one orbit. So it does one pass, downloads 2 weeks of data, does another loop, downloads 2 more weeks of data, and then it moves on to a new part of the sky. And currently, TESS has just begun its 7th section of the sky. So it's about halfway done with the first year of the 2-year prime mission, just so everyone's aware of what the status of the spacecraft mission is. Oh. Let's try this. So here's the spacecraft. You can see the solar panels on the wings. The dome on the back is the radio that it uses to communicate with Earth and download its data. And the most important part of the spacecraft are these 4 cameras in the cone. This is what TESS uses to measure all the fluxes and look for exoplanets. How does it detect exoplanets? It uses a technique called the transit method. And conceptually, it's one of the simplest ways we can discover new planets around stars. We measure the brightness of stars very, very, very carefully and literally wait for an exoplanet to cross in front of it and get in the way. The challenge is that the amount of light that a planet blocks is very, very tiny. So you have to be able to measure brightnesses of stars very, very carefully. It's taken decades of us to get to where we are today, but we're able to do so with a lot of great success. You'll notice in this animation there's 2 different planets, sort of as to show you what the signals might look like. This is sort of what happens if someone walks in front of a projector in a movie theater. They'll block out part of the light, and you'll see that the screen that was bright is somewhat less bright. But you'll notice that we can actually model a lot of the interesting parts of a planetary system just by looking at the shape. The depth of the transit decrease in brightness, how long it lasts, even details like the shapes of the beginning and ends can tell us a lot about the planets, the stars, and the orbits of those planets. So let's go back to the cameras real quick. There's 4 of them, like I mentioned, in that cone area. And each one is surveying a large chunk of the sky. And I really want to focus on how big TESS is, because it's very, very different from other telescopes like Hubble. Each camera is 24 by 24 degrees on the sky, and there are 4 of them aligned so that they stack on top of each other on the sky. So when TESS is collecting data, it's quite literally observing this orange wedge that's more than 90 degrees of the sky at a time. So we'll do this with our 4 cameras for 2 weeks, download the data, do it again for 2 weeks, and then after it's done with 2 orbits of collecting data with its cameras, and it starts the next sector, as we call it, it will actually move a little bit on the sky and end up surveying this hemisphere on the sky. So it'll take about 1 year to do the southern hemisphere. Starting sometime this summer, it will finish the first year. We'll literally flip around and we'll survey the northern part of the sky. One key part to notice is that as it's sweeping out and observing lots of stars along the sky, one of the cameras, camera number 4, actually stays in the same part of the sky. Every single time TESS observes, this one camera is always going to be at the pole on the bottom, and when it flips around to the north, it'll be in the northern pole. This means that any target, stars, galaxies, whatever, that happen to lie in camera 4 will get observations every single month. It will get a full year of continuous data. We call this a continuous viewing zone. And I bring it up because this sort of emphasizes the foresight of people planning TESS working with James Webb. Because these continuous viewing zones that get a year of solid data in the north and south overlap with James Webb's continuous viewing zones. And this was very much done on purpose, so that when James Webb launches, it will be able to observe any target in TESS's continuous viewing zones anytime the schedulers decide it makes sense. And this is an example of the synergy between TESS, the tiny planet finder, and Webb, the giant planet characterizer. So this is where I'd like to do one more comparison with Hubble, in this case, and TESS. So this is a picture of another star cluster. Frank described some of these clusters before. This particular image is a Hubble image of a cluster around the Large Magellanic Clouds. This is a very nearby galaxy, unlike some of the ones that Frank was talking about. But it's still impressive that Hubble is able to actually resolve individual stars in this cluster around another galaxy, albeit one that's very close to the Milky Way. Nevertheless, to compare it for scale, here's a picture taken from a ground-based telescope of the entire Magellanic Galaxy. So this is a neighboring companion galaxy to the Milky Way. And what you previously saw in the Hubble image that I've since shrunk and stuck over here in the corner, that nice, beautiful picture of all these stars, is really coming from just one little bright bump in this ground-based telescope picture of the entire galaxy. All these bumps are things like stars and star formation regions and star clusters and a bunch of dust, a lot of interesting structure. So you can get a sense of exactly how powerful the resolution is of Hubble compared to the ground. But TESS says, hold my beer. This is the 4 cameras from the first sector. This is the entire Magellanic Cloud galaxy contained easily in 1/4 of one of TESS's 4 cameras for scale. This little blur over here in camera 3 is a small Magellanic Cloud. And every single little dot you see here, every single one, this is not noise, these are not cosmic rays, these are not television screen that the cable went out on. Every single one is a star that might have a planet around it. So you can see what the game that TESS is trying to play. It's not going for high definition. It's going for screen size. One last point on this. This is the smallest smallest square I could draw with PowerPoint. It wouldn't let me draw a smaller one. But this is supposed to represent the area of sky that the Hubble Wide Field Camera 3, now back in operation, would see with its instrument. The size of a TESS pixel on the sky is 525 times larger than the size of a WIF-C3 pixel on the sky. And so that is this square. So 1 pixel from Wide Field Camera 3 on Hubble is this much part of the sky, but on TESS, 1 pixel from TESS is this much part of the sky, to give you a sense. And it's not really a game we're playing about which is better or worse. They're different and for good reasons, right? I like to think of Hubble sort of operating like a powerful microscope does, where it's being able to resolve and reveal things like tiny creatures in a drop of water, while TESS is more like a surveyor that's really trying to chart the ocean itself. Different objectives, different decisions on pixel sizes. So let's go back to our first set of real data. These are real images collected and downloaded and now public from the spacecraft. You notice the Large Magellanic Cloud, the Small Magellanic Cloud, lots of stars. One of the things, the bonus science that TESS is doing, is that astronomers are looking at all kinds of other physics that are happening within these huge fields of view while TESS is looking for those transiting planets. So I showed a couple of pictures of asteroids and comets. There are going to be tons of asteroids and comets that astronomers will be analyzing from the TESS data. Another great example are supernovae, exploding stars. Because TESS is staring at the sky, and a huge part of the sky, it doesn't care whether it's on time or late for a supernova to happen. It's just going to be in these huge fields of view. And so one of the initial science results that were presented just last week at the AAS were some of these supernovae that went off while TESS was observing. There are actually 6 different supernovae that happened and discovered by telescopes on the ground, specifically named the Assassin Survey, which is one of my favorite names for a survey, and the Atlas Survey. And these telescopes found a supernovae by looking at relatively small parts of the sky compared to TESS and noticing that something here that wasn't there before. And so they send out an alert to astronomers. And so usually astronomers will rush to a telescope and try and get more data once the supernova happens. But in TESS's case, it says, don't worry about it. I've been looking at this and everything else for a long time. And so astronomers, as soon as the data were downloaded, are able to use the TESS light curves to get these beautiful plots of how the supernovae are changing over time. This is just another example of what you can do with TESS data. A lot of people probably heard of Kepler, or K2, I hope. Kepler really revolutionized our understanding of exoplanets, but the Kepler mission has since ended. Spacecraft was retired and shut down due to a loss of its gyros and the ability to control itself. But it's really a bittersweet ending because the timing couldn't have been better. It actually lasted much longer than the original mission was originally funded for, and it ended not too long before TESS started. And so really Kepler and K2 are sort of, that mission is sort of passing the exoplanet torch to the next NASA mission, which is TESS. And I mean that quite literally because the TESS data reduction pipeline is actually mostly the Kepler pipeline with tweaks. That's how much Kepler revolutionized our ability to measure these planets. Just to highlight again the impact Kepler had, this is a little cartoon that sort of shows all the multi-planet systems that Kepler found over its 4+ years of operations. And you can see it discovered all kinds of interesting planetary systems, some of them having 2 planets, some of them having 4, 5, 6, different sizes, different distances from their host stars. And it's just really a cornucopia of exoplanets that were detected by the Kepler and then later the K2 mission, which was sort of Kepler recycled, if you will. But TESS is going to really go one step further. So this is the Kepler field of view in yellow. That's one camera from TESS. One camera is twice the size of Kepler's entire field of view. There's 4 of them for every single wedge. Every month we get basically 8 times the size of Kepler. We're going to do that for 2 years across the entire sky. So while Kepler detected a lot of exoplanets looking very deeply at these gold areas of the sky, TESS is going to mow the lawn and discover all kinds of planets around the wide part of the sky, but around brighter stars. So here are the first 3 systems that have been not only discovered, but verified. And I'll go through each one in turn. You can see the locations of the host stars on the FFIs, which are these full-frame images for short. Here's Pymen C's location, LHS 3844, and HD 21749. You'd never be able to tell these apart from any other one unless you sit down and look at all the measurements and figure out which ones of these things are twinkling in ways that we care about for exoplanets and which ones are doing other things and which ones are doing nothing. That's the beauty of TESS. So let's start with Pymen C. So this is a very interesting host star. It's actually pretty close by. It's about 60 light years away. This is going to be a common theme, by the way, for all three planets. It's so bright that if you're in the southern hemisphere, say you go to Chile or Australia or something, you can actually see the star with your naked eye in the southern hemisphere. That's how bright and close the star is. The star itself is pretty similar to the sun. It's about 10% larger in mass and size compared to the sun. And the planet is one of these really interesting examples of something we don't have in the solar system. The planet's radius, the size, is about double that of the Earth, and the mass is about 5 times the mass of the Earth. And there's no such example of this in our solar system. We sort of jump from Earth all the way up to the ice giants, Uranus and Neptune. The orbital period is one of these characteristic short period planets. It takes about 6 days for it to do one complete orbit around the star. So it's very close to its host star, much closer than Mercury. An important point is if you can measure the mass and the radius for the planet, which we have done in this case, you can take mass, divide by the radius cubed, and you get something called density. And this is sort of an average density, but it allows us to make very basic claims about what the planet might be made out of. We can show, for example, that based on our measurement of the planet's mass and radius, it cannot be made entirely out of iron, for example. It cannot be made entirely out of gas, for example. In fact, we are able to identify that the planet is likely a combination of rocky material and probably some kind of gas. We don't know whether it's a hydrogen-helium atmosphere or perhaps a water or methane atmosphere. It might be thin, it might be relatively thick. This is where follow-up observations are needed, including from James Webb. The other quick thing I'll mention is that there was actually another planet that was previously known around this star. Orbiting much farther away, it takes 5 years for that planet to go around Pymen star, and it's huge. It's 10 times the mass of Jupiter. It's almost a star in its own right. So the first exoplanet discovery by TESS was actually a second planet in a known system, which is really interesting. And there's going to be a lot more of these as time moves on. And the plot on the right is taken straight from the paper that announced the discovery of this. On the axis up and down is basically a measurement of the brightness of the star as a function of time. And you can see, if you remember back when I showed the little animation of what happens when a planet goes in front of the star, we see a very characteristic drop in the flux while Pymen C is going in front and blocking all the light, and then it goes back to normal again. So these kinds of plots, which we call light curves, are what we really want to get out of TESS to then study and measure properties of the planets that we find. Here's the second planet, and it couldn't be more different. So again, we have the characteristic shape of the brightness of the star sort of sitting there being fine, and then, oh, hey, it drops down. There's a planet blocking this particular star. But the host star is very, very different from Pymen. LHS 3844 is what we call an M dwarf. It's very, very small. It's about 15% the mass of the sun and about 20% the size. So it's a very tiny star. It's red, it's cool, and they are some of the most interesting targets for exoplanets and habitability in our solar system. But the one thing it does share in common with the previous planet is it's close. It's about 49 light years away. And it may seem far, but when I compare to other known planets, it's actually pretty close by. The planet itself is about 30% larger than the Earth, so it's pretty small. What's amazing is that it takes 11 hours for this to orbit the star. Half a day is 1 year on this planet. For context, Mercury, the closest planet to our sun, takes 88 days to go around the sun. This thing takes 11 hours to go around this star. Remarkably short orbital period. Because it's so close, it's not a nice place to be, even in January. The temperature on this planet is something like 1,000 degrees Fahrenheit, estimated. Not to mention that it's being bombarded by all kinds of ultraviolet rays and gamma rays. The atmosphere has probably been baked off, so there's no protection at all for anybody who might be on the surface. It's a horrible place to be. But in the context of understanding how planets form around stars, it's vital, because we want to understand how is it that you got to where you are. It tells us a lot about how planets form and how they change over time. The last exoplanet that was discovered and was recently announced is HD 214079. And it's interesting because, once again, it's sort of in between the types of planets from the previous two. Again, it's very close. It's about 52 light years away. So all three are very close to the sun in terms of other stars. It's in what we call the solar neighborhood. This star itself is sort of in between the previous Pi-Men's planet host star and LHS's host star. It's about 75% as massive as the sun, about 70% its size. So this is what we call an orange K-dwarf star. They're very interesting in their own right. The planet is sort of what we call a tiny Neptune or a sub-Neptune. So it's an ice giant, we think, but it's somewhat smaller than Neptune. It's about 3 times the size of the Earth, about 23, 25 times the mass of the Earth. So it's probably some sort of ice giant, perhaps a little bit smaller than what we have in our solar system. And it takes 35 days to orbit its host star. Still within the orbit of Mercury, right? But compared to the other two, much further away. The other interesting thing about this system is in the discovery paper, there is evidence of a second planet in this star system that is actually very, very similar to the radius of the Earth. And if we can measure its mass, this might be the first Earth-sized and Earth-mass planet discovered by TESS. Not habitable, because the orbital period is only 8 days, so it's getting baked just as much as anything else, but it shows we're able to find these and perhaps be able to characterize the atmospheres of some of these planets that are similar to the Earth in its size and its mass. Very exciting, so we should stay tuned for more information about whether the second planet signal is real or a false positive. Just to highlight again the differences, tiny, tiny planets compared to huge Neptune planets, no atmosphere and boilingly hot around a red M dwarf, sort of a tiny Neptune orbiting an orange K dwarf. Then we have Pi-Men, which is this weird sort of super Earth class planet that we don't really have examples of in our own solar system, but orbiting a star that's pretty similar to the sun. So these first three, by themselves, really show the diversity of types of planets around different types of stars that we're going to find in TESS. And there are hundreds of other candidate planets that astronomers are following up right now with telescopes from around the world. And this is just from the first couple of months of the 2-year mission. So stay tuned. There'll be a lot of new discoveries coming in 2019 and 2020, for sure. Just to highlight this fact even further about how important it is to discover nearby planets, here is the location of the sun. And these little circles sort of show distances away from us, right? So this circle represents 10 light years away. This circle is 30 light years away. And as we go further and further out, we get more and more stars in our neighborhood. And so the location of the first 3 planets, you may have noticed, they all have roughly the same distance. They're all roughly the same distance away from the sun. They're pretty close by. If I add some of the previously discovered planets, you can see that these 3 that have come out are already sort of in the top 10 or 20 closest planets we know about to the sun, which is already exciting, and there's going to be a lot more coming. In fact, we can make some predictions. So this is a simulation where we know which stars TESS is observing, and we know how common planets are, and so we can predict roughly how many stars near the Earth will we detect planets around. You can see TESS is really going to fill in the really, really close by known planets that are discovered. And as we zoom out to further and further distances, you can see TESS is really going to fill in all of the known exoplanets that are as close to the sun as we can get. In blue, you actually have the Kepler detections. And you see that while Kepler discovered lots and lots of planets, unfortunately, a lot of them are really far away. And so while we can detect them and measure some basic properties, what we really can't do very well is get follow-up data to really characterize what they're like. Try to measure atmospheric compositions. Try to predict whether there's strong winds on some of these gas giants, things like that. So the TESS discoveries, which should fill in this yellow space, are designed to do exactly that. This is one last way of showing this point. So on the up and down direction, you have the size of discovered planets relative to the Earth. So this is one Earth radius. This is a planet that will be twice the size of Earth, 3 times the size of Earth, etc. And on the left and right direction, we have distance away from the sun. So in black are some of these previously discovered planets from the ground primarily that have been orbiting really, really close stars to the sun. And in blue, we have the Kepler and K2 discoveries. And one thing I hope you'll all notice is that they're all on the right of this plot. A lot of them are far away. They're 300, 500, maybe even a few thousand light years away, which make it very hard to study them in a lot of detail. Here's where those TESS predictions come in. TESS is going to find lots and lots of small planets, 1 times, 2 times, 3 times the size of the Earth, orbiting only 30 or 50 or maybe a few hundred light years away. And these are the ones we can really follow up with telescopes like Hubble and James Webb and from some of the most powerful ground-based telescopes around the world. So I wanted to leave you with a quick summary. The first public data release has happened here in Baltimore. If you're from Baltimore, you can be proud to know we're the home of TESS long term. The first TESS exoplanets have been discovered and published, and I shared with you the first 3 that have been published. There are hundreds of exoplanet candidates actively being followed up by astronomers around the world as we speak. So there'll be a lot more discoveries coming in the next few months and even the next 2 years. The spacecraft is very healthy. It's actually starting its 7th sector just a week ago. Observations are ongoing. Data are being downloaded from the spacecraft to Earth every 2 weeks. And the initial discoveries in other areas of astrophysics are happening now as well. We have asteroids and comets, all kinds of stellar astrophysics, supernovae, all kinds of bonus science. So what's really interesting is that every single one of these planets that we find with TESS are going to be new worlds around nearby stars. And as an exoplanet scientist, we are super excited to be able to work hard every day to confirm as many of these as possible. Because after all, we think it's, by far time for us to meet our neighbors. And that's what we're doing. So thanks for your attention, and I'll take any questions you have. Yes, so I have a limited supply, because this is all I could steal from the meeting, of TESS mission stickers. But if you'd like one after the question session, feel free to come up and grab one. And if we run out, I may even try to pilfer some more and give it to Frank for maybe a future meeting if you can't get them all out.
It'll be available on eBay for a good price.
Okay, start from the very left.
Let's start over here. How about you? Wait for the microphone. It's going to come around.
Who's coming?
Very simple question. What is the diameter of that orbit of TESS? Did you say?
That's a good question, and that really tests my limit of the orbit of the spacecraft. I want to say it doesn't go much further than the lunar orbit, but I'm afraid I can't answer with any definitive question about it. Yeah.
All right. But that prompts my comment. there was a talk given just recently here about that orbit, and I was just flabbergasted at how stable that
Yeah,
orbit is.
I was going to mention that. Yeah.
Yeah. Could you just tell these people?
Sure.
I mean, it's
So-
stable for like 20, 30 years or
No,
something.
no. So this is actually sort of along my line to sort of, if you're excited by TESS, to advocate. So the primary mission will end in 2020. There is opportunity for us to ask NASA to fund TESS to do another 2 years, and another 2 years, and another 2 years, as long as NASA is willing to support the funds. The orbit of TESS is actually balanced with something called a quasi-light-off mechanism. Because SpaceX did a bang-on job of getting it to where it wants to go without using much fuel, and the orbit is so stable, the spacecraft has enough fuel to last for 300 years. Minimum. So suffice it to say, it will not be fuel that causes TESS to stop taking data. We will either have a hardware failure, or at some point, NASA will make a decision to retire the spacecraft and move on to another project. But there is every indication that TESS will be able to extend not only up to James Webb Space Telescope launch, but even past James Webb Space Telescope launch, finding planets, studying stellar astrophysics, finding comets and asteroids.
So that's an orbit. Okay, who's got the microphone? Yeah.
Hi. So I have a two-part question about the simulated or the predicted locations of planets. The first part is, how did those predictions map to the graphic that you showed us, as that was two-dimensional? And I didn't quite get like how that. I guess it was before this in the presentation. Yeah. Yes, I believe it was this.
Yeah. So. Yeah.
Oh, and sorry. The second part is then. What is the second part? Is the angle a significant part of the simulation, or is it? Yeah, I guess like how did you choose what spots chosen in the simulation?
Yeah, those are two good questions. So the orange points here do correspond to the orange points on this two-dimensional plot. And the simulations are statistical, right? So they're not necessarily guaranteeing that so-and-so planet will have a star. It's sort of a random simulation where we know which stars and what types of stars are in our field of view. And we have some good numbers from Kepler and from the ground of how often certain types of planets are found around them. So this is one instance, if you will, of TESS's predicted yield. We could do a similar calculation with a slightly different random number and have the orange circles themselves be around different stars and different angles. But the key point is that the number and overall distribution will be roughly similar. So we could run this 100 times, but the point is you still have orange points primarily all around here. You'll have very few out here. You'll have very few way over here. And so it's just sort of an estimate of the yield. And so don't worry too much about which individual star has a predicted planet around it. It's the total number and the overall distributions. Yeah. Yeah, and in fact, although I don't have the data at the meeting, they overplotted on this the initial candidates that are actually detected around the actual stars, those few hundred I talked about. And indeed, they do sort of overlap right in this region. So we're in great shape for that.
So there's a question online about focusing on, like, the Gliese catalog goes out to 25 light years. And so it sounds like we're going to get maybe 5, 6, half a dozen of them inside 30 light years. And those, of course, will be, very prime for follow-up because they're so close.
Yep. So the target selection was a multi-year effort, of which I played a very small part in. But indeed, we had to do a lot of work before the spacecraft even launched to figure out which targets we want to get the best, most sort of the fastest measurements on to look for planets. And so we indeed are observing pretty much every M dwarf we know about that's bright enough to get the signal that we need to find planets around, because M dwarfs are so interesting. And then on top of that, we're also observing as many of the best sort of solar-like and those K dwarfs I mentioned, the orange dwarfs, that are close by and are relatively well behaved otherwise. They're not particularly noisy or have other bad features about them. Mm-hmm. Yep.
Okay. Other questions?
Is there a greater likelihood that TESS will find shorter period orbit planets rather than longer period orbits?
Yep. Of course, it depends on what you mean by short and long, but the minimum baseline for a given star in TESS, for the first 2 years at least, is about a month, because it takes one of those orange wedges. Now, if you're lucky and you happen to be a star that lives in the poles, you'll actually get 12 months of coverage. And so you can find orbital periods out to several months. But you are right. TESS is not really designed to measure the question Kepler set out to do, which is to ask how many one-year Earth-sized planets are there. TESS's job is to find lots and lots of Earth-sized planets that are orbiting very close, so we can actually probe the atmospheres of them with James Webb. And it turns out the best candidates for that are planets orbiting bright, nearby stars, as close to the star as they can get, so you can get lots of samples.
Other questions? We had a question from online. The continuous viewing zones. Sometimes those are pointed at the north and south galactic poles. How are they situated?
Ecliptic, yeah.
They're now the ecliptic?
Yep.
The ecliptic poles. Okay, so that was the question online, was where the CVZs are located.
Yeah, sorry, I didn't know if I wanted to go into ecliptic versus, but essentially the.
We got some geeks online.
Sure, no, that's awesome. That's great. So yeah, I want to try to get to the movie that shows it, but if not, they can go back. The TESS in the first 2 years is avoiding what we call the ecliptic plane, which is where the majority of our planets orbit around the sun, and a lot of the asteroids and comets, though not all of them, are sort of located. It's actually avoiding that for the first 2 years. But there's a potential to go and get those in the next 2 years. And that's something we're thinking about very hard if NASA funds us for 2 more years of observations. But yes, it is the ecliptic poles where the CVZs are.
Good.
Thank you for the question.
That was my question.
Oh! I should have added a slide about it.
Beat you to it.
I love it when a plan comes together.
Other questions? We had a question over here.
Ready? I'm just interested in how this data can feed into changing the Drake equation.
That's a great question. We always say TESS is not a statistical mission. Kepler's prime science objective was to try and do a complete survey to sort of answer questions like, how many stars of type X have planets of type Y? That was its primary objective. The targets and the whole mission design were designed to answer that question. TESS's question is different. TESS is not worried about completeness, and although people will do statistics on these things, it's not really even sensitive to a lot of the habitable zones, with the possible exception of those M dwarfs, because the habitable zones are so much closer. Instead, TESS is really finding as many of our nearby short period planets of all kinds of sizes for 2 reasons. One, to understand which of our solar neighborhood friends or solar neighborhood stars have planets around them, and they may have planets further away if we do follow up. And 2, to enable things like James Webb and Hubble and the most powerful ground-based telescopes to basically detect the compositions of their atmospheres, which is arguably one step of the Drake equation, if you want to call it, but it's not really sort of measuring A to Earth, if you've heard that before. That was really Kepler's role, yeah, if that sort of addresses your question. I'm happy to talk more as well if there's time or after. Yes. So, yeah.
The number of stars with planets.
So this will actually sort of, we expect to find comparable number compared to Kepler. The difference, of course, is these stars are much closer to us. So it will give us a good census about planet frequency around neighborhood stars.
Do we have a question here?
So I was once told that if you were looking at stars, what would happen if you had an ocean? And I was told that basically oceans were where photons went to die. Is that still true? Would there, if you happened to find a star or a planet that had an ocean on it, you're still not going to be able to see it? Or
for the atmospheric composition questions, or
well, like actual ocean, water ocean.
Oh yeah. So for detecting the planet, it's pretty insensitive because the way we're detecting these planets is we're just asking, is there something in the way? And whether there's a pure water world or rock or iron or gas, doesn't matter. It turns out it's going to block the light, and we're going to see a decrease in the brightness of the star either way. The challenge comes with the atmospheric composition. There's a couple of factors that sort of dictate how well we can really measure the atmospheric composition and even size of these planets. And one of them is how thick is the atmosphere. As you might imagine, the thicker the atmosphere, the more atmosphere the light has to travel through to get to us, and so we have an easier way of measuring some of the details about those properties. For pure water worlds, it can be sometimes a challenge because a lot of light might bounce off of the atmosphere before it gets to us. So yeah, that's one of the reasons why we want to find lots of them, so that when James Webb is operating in a couple of years, we can have it start off with the best candidates instead of sort of spending a lot of time on some of these water worlds or other things that might not have as good of a chance of us detecting atmosphere around it.
Okay, so we have a question from online. How sure are you that these light curve dips are planets? Could there be other phenomenon that mimic this, and how do you get rid of these false positives?
That's a fantastic question. It's actually the subject and careers of several astronomers, myself included, actually. I've been a co-author on papers that have disproved planets and ones that have proved planets. It's actually a multi-telescope and multi-technique method. But so we can do a lot from just the shape of the light curves themselves. We've learned so much from Kepler and K2 and other ground-based systems. You can actually do a pretty good job of weeding out false positives, and there's a variety of those. Some of them include just artifacts that are not even real. A big one are eclipsing binaries, which actually I'm interested in scientifically, but all the exoplanet people say they're junk. And I go, no, they're not. I want to do cool stellar stuff with eclipsing binaries. But the problem is they can sometimes look like planets when they're not really. So there's a couple of ways to avoid that. One of the best ways to really know if a transiting object is a planet is to look for what we call the Doppler effect, or the radial velocity method. And you may have heard about this before, but it's a different technique. It requires telescopes on the ground, and the way that works is once we see a signal with a dip, we then have the hypothesis that this is caused by a planet. If it's a planet, what happens is the planet's orbiting around the star. I'll illustrate, right? Because it's being tugged on by gravity, right? Gravitational pull of the star on the planet is having this thing go around. But Newton's law tells us there's an equal but smaller effect of the planet on the sun. So if you have a very, very precise instrument, you can actually look for myself as the sun now being pulled toward the planet a little bit, very little bit, but nonetheless measurable as the planet goes around it. And so if the planet's in front of me, I get pulled a little bit toward it, and now it orbits over here. Now I'm pulled a little bit over here. Now it's behind me. I'm pulled a little bit toward it, right? And so we end up having this wobble of these stars. And you can actually detect that, believe it or not, with instruments on the ground. The effect, sometimes the effect we're looking at is slower than me walking. That's the size of the signal we measure with some of these instruments. But we're able to do that with a lot of experience and with very big, powerful instruments from the ground. So that's the best way we have of detecting it. And indeed, a few of the ones I mentioned have been confirmed by that method.
Okay. Other questions here? One way in the back, just to give you some exercise, Grant.
Thank you for running with my cube.
So I was kind of interested in how you said that it sounded like a lot of these, or most of them, can be looked at. You said they're going to follow up with telescopes from Earth.
Yep.
So are these things that could have been seen anyway without TESS? So what's TESS doing? Is TESS just helping them find them quicker, or?
That's a great question. There's a couple of parts. Some of these are not able to be found with our current instruments because some of the things like the wobble I mentioned that they induce is just too small. We can't even see them still. The other thing it does is the field of view. Most of the instruments I mentioned, especially the ones that measure wobble, have to look at one star at a time, and it has to monitor it for usually several days and get dozens of measurements before it can really show that it's a wobble that's happening. There's 200,000 stars just in the high priority list. So 200,000, one at a time, you only have a certain number of nights per year because the telescope's being used for other things. It becomes impossible to do the size and scope of the search from ground-based using those methods. So you're right. Your idea was exactly right. TESS is, a large part of TESS is being able to detect a lot of these small planets using the DIP technique, the transit technique, with a huge net. And then we can take the expensive part, which is going to these huge telescopes on the ground and getting these expensive measurements that cost a lot in terms of number of nights and all this other stuff, to then confirm them once we know there's a signal there. We don't want to have to look at 100,000 stars that aren't doing anything. That's not a good use of our telescope time. Yep. Great question, though. Thank you.
Okay, I think we got time for one more question. You've had a question. Is there anybody else? All right, come on down here. We got this gentleman's got another question. We'll finish off here.
I'm interested in the effect of the orbital period of the planets that we're detecting. As a thought experiment, I'm thinking if another solar system someplace out there was looking at us, if our period's 1 year, if you didn't happen to be looking at Earth when we occulted the sun or transited the sun, you'd miss it. If you were looking for Jupiter, it's once every 12 years.
Good luck, right? Yeah, yep.
And so, how do you allow for that? What adjustments do you make for that?
That's a great question.
And given the lifetime of the current funding, how long of a period can you see in these planets?
So that's a great question. And the way we get around it is twofold. One, we go to space. In space, there's no pesky thing called the day-night cycle. On the ground, when it's daytime, you can't observe because the sun's up. Space, you can observe all day, every day, and just stare at these things and get lots and lots of measurements because you don't know when it's going to happen, right? So A, we look at them all the time during the time we're taking data. Two, we do it very quickly. So we're constantly measure. It's almost like OCD, right? Measure. And then the third point was about the solar system. So again, Kepler lasted 4 years. And so it was able to, during the prime mission, right? It was able to see a signal, at least one, during a 1 year orbit. Most of TESS will not be sensitive to things like that. So we won't be able to see things that have 1 year periods during the prime 2 year mission. But if NASA decides to fund TESS for 2, 4, 6 more years, now we have enough observations that we will be able to see single dips caused by something that might be very, very long period. And because we have so many stars, we're such a huge part of the sky, even if we miss 99% of the Jupiters or something like that, we just need to find one and then follow it up and have some patience, and we'll be able to find things potentially like Jupiters at 5 AU that take 25 years to orbit. You look at a whole bunch of stars, you have the one at the right time, you might be able to get it.
Yeah, and that's a great perspective on this because you realize that we've only been discovering extrasolar planets since 1990s. So we got 20 years. Saturn takes over 30 years to orbit the sun. We could never have found a Saturn in a Saturn-sized orbit
with this technique.
With this type of technique. So, exoplanets are only going to get more interesting. I think Scott has provided us an absolutely wonderful presentation on TESS, and we can't wait for more stuff. You're going to come back next year and tell us.
I'll be here next year and I'll have a lot more plans to talk about.
All right, you heard him, folks. Let's give him a great big hand.
Thank you.